pressed record. I think we're good to go on Zoom. Colin is joining us. Let me know if you can't hear us. All right, so we're talking about electronic effects on a molecule's stability. And this is kind of fun because you get to see where some of the things we've been learning about orbitals actually have some control over the shape and properties of molecules. So we're going to begin with a minor electronic effect that you've heard about before, and that is alkene substitution. You've heard that more substituted alkenes are more stable. And the reason that you've probably been told that before, I'm trying to figure out. Probably, if you've been told anything other than to just memorize it, it has been that there's this possibility for hyperconjugation when you have protons or other groups alpha to the carbonyl. So here is a CH bond alpha, to the double bond. It applies for carbonyls too, but we might envision, that filled carbon-hydrogen sigma bond, again from a valence bond perspective, donating electron density into the pi star on the alkene to give, and this process would allow the electrons in the carbon-hydrogen bond to move down lower in energy. It would also delocalize the Lumo and move it higher in energy. So we've called that before sigma to pi star hyperconjugation. And it is an example of what your book calls a donor acceptor effect. And this is a filled orbital overlapping with an empty orbital in the same molecule. And again, we're considering orbitals here in sort of a valence bond perspective to be localized between atoms for sigma bonds. Some delocalization allowed for pi bonds. But if you imagine mixing a sigma with a pi star, the principles that we learned from orbital mixing in our qualitative molecular orbital theory still apply. That is, there's an energy gap between these two orbitals, and in some cases it's quite large. So the bonding orbital moves down a little bit in energy. The anti-bonding orbital moves up a little bit in energy. The bonding orbital still looks a lot like, the new bonding orbital would still look a lot like a sigma bond, but somewhat spread out onto the pi bond, and the sigma star would the pi star would still look like the pi, only spread out a little bit into the sigma area. Okay? And that is a stabilizing effect, and the more you have of them, the more stabilizing the molecule is. Why is it a stabilizing effect? Because from a valence bond perspective, when you mix a filled orbital with an empty orbital, the electrons in the filled orbital move down in energy. Okay? I've had students ask before, aren't you dumping electron density into an antibonding orbital, and shouldn't that break a bond? And I feel like that's a good question, but I think it comes from a mistaken premise, which is we're not taking the electrons and populating the antibonding orbital. We're just mixing two orbitals together, and we have the same number of electrons. And so we've still got a bonding orbital, we've still got an antibonding orbital. You can do look at alkene substitution from a valence bond perspective. From a molecular orbital theory perspective. I've got, in the notes I've posted online, I've gone through and drawn what the MOs are for propene. It turns out they're not actually that different from the allyl system. if you imagine propene is only one proton away from being allyl anion, and so the MOs are qualitatively similar. So if we were to go over to Spartan here and clear out everything, let's just get a sense for where double bond pi orbital is. Let's get the energy diagram. Pi bond, minus 7 electron volts. That's the HOMO of the molecule. You've got other sort of carbon-hydrogen sigma kind of, well, this is the out of phase pi CH2 plus pi CH2. This is the sigma outs and so on. Let's just compare that with adding a methyl group. And again, I want you to remember the number on the HOMO, which is minus 7, and maybe, yeah, that's fine. We'll go back and look at the numbers if we need to. Let's just add a methyl group and see what that does to our energies. The HOMO goes up in energy, but there are other orbitals that are moving down in energy. In particular, this one. This is the orbital that looks like it's the looks like it would be the carbon. It looks like the carb. What am I trying to say here? The pi CH, one of the pi CH3 groups, the one that has a proton in the node, but it's delocalized onto the part of the molecule where the pi system is. So this is an MO that sort of tells you what hyperconjugation told you. Electrons that are normally would normally otherwise be considered primarily CH bonding are indeed spread out onto the alkene. Also, in order to calculate the overall, remember that even though the HOMO gets higher in energy, and this is a subtle effect, right? I'm sorry, I'm going to back off and get rid of the methyl group. You're going to look at the energy of the highest occupied molecular orbital again, minus 7. And then you're going to notice that when we add the methyl group, the energy of the highest occupied molecular orbital actually goes up. And that correlates with another observation that more substituted alkenes are more electron rich. But why do we say more substituted alkenes are more stable? Because overall, remember, to calculate the stability of the molecule, you've got to add all of the energies of all of the orbitals times however many electrons are in each orbital. And if you make that comparison, you can come to the conclusion that more substituted alkenes are more stable. All right. Yeah.
So when you were drawing kind of the energy diagram back in your notes, you had
Sorry.
the pi star, the empty pi star increasing in energy.
Yeah.
Does that have any impact on the orbitals that went into forming the pi star?
So yeah, the question is, when you do this hyperconjugation, this mixing of sigma and pi star, the pi star goes up in energy. Is that reflected at all in the orbitals that went into forming the pi star? Is that your question?
Yeah, I guess originally the pi star was formed by two original orbitals that give the pi star in the bonding orbital.
Right.
I guess more accurately, does that impact the bonding orbital that was formed opposite the pi star?
Oh, does this hyperconjugation influence the bonding orbital that was formed? There's a pi down here that we haven't even talked about. That's a good question, and frankly, you can drive yourself a little nuts trying to keep track of what's affected by what with hyperconjugation, as though you could turn it on and off. Remember, hyperconjugation is sort of a patch we apply to valence bond theory, or at least our simplistic understanding of valence bond theory, to get us to the same place that MO theory gets us. And again, if you do a full treatment of valence bond theory, you get exactly the same answer as MO theory. It's just conceptually, if we want to think about Lewis structures in order to get to some of the reality of organic compounds, we've got to use things like resonance and hyperconjugation. I guess if you want, this is, okay, I will do this only for the pi-type orbitals, okay? So if the best way to think about constructing the, and I'm going to talk about the pi orbitals that are coming in and out of the page, right? Because we've got pi-type orbitals that are in the plane of the sigma bonds, as we know from quantitative or qualitative molecular orbital theory. But if you wanted to make the pi-type orbitals together, you're going to be of the sort of system and include the ability of the CH3 to participate, you're going to be mixing a p orbital on carbon 1 with a p orbital on carbon 2, and then you're going to be mixing the corresponding pi CH3 on carbon 3, okay? And in effect, we're going to get exactly the same sort of thing that we got with the allyl cation. We can mix them all together in phase. And if we draw just sort of a top view, I'm sorry about the squeaking. This little plexiglass thing maybe is squeaking when I write. Maybe that's why Vice President Pence doesn't want to use the plexiglass at the debate tonight. Maybe he's concerned about the squeaky. All right. So this is what one of those, the lowest energy pi orbital looks like, at least if we were to draw it. Though we would need to note that the pi CH3 is definitely lower in energy than the p orbitals, and so we would expect this orbital to sort of be biased toward carbon 3, right? And that's what we see in Spartan when we look at that one. Okay. Where's the next one? Well, remember that, let's see, the next one should come from when we were doing allyl cation, we came up with something like this for our middle orbital. You could do p plus p minus pi CH3, because this is the all plus version, if that makes sense. Or you could get p minus pi CH3. The fact that the CH3 is not the same as the other two carbons breaks the symmetry of the system, and what you end up with for that orbital, if you do the calculations, is a node here. Oops. And so there's a phase switch. And incidentally, that's why our highest energy filled orbital is this one, which looks like a pi bond and then a phase switch and then the methyl group. Yeah?
This is just a little off topic. Is there any nice way to distinguish between the two different pi CH3 orbitals, the NH3 thing? Because there's the one where you have the hydrogens in the node, and then there's the one where all the hydrogens are in phase.
I suppose you could come up with a way to do it. I mean, with p orbitals, we've done that because they're orthogonal, px and py and pz. So I suppose we could call one of them x and one of them y,
Okay.
and that could work.
Okay. Yeah.
Or you could just remember we have two of them and they're orthogonal to each other.
Right.
Yeah. Okay, and then our last example, which I won't show you because who cares, is the one where they're all out of phase, and that's the Lumo of the pi system. And remember what our hyperconjugation picture told us. It said the Lumo is going to look mostly like the pi star, only there's going to be some on the adjacent carbon hydrogens, and that's exactly what the MO picture gives us. And what I'm showing you here is exactly what we would get by doing the, it's only a small color change, so I guess I'll do it. The sort of minus then plus combination. So, bloop, bloop. All right. So this is the one where you have the 2 nodes. So this MO picture gets you where hyperconjugation gets you. From the MO perspective, it is not at all apparent that substitution increases the stability of the alkene unless you go and populate all of the orbitals with electrons, right? And calculate the energy. And then remember, when we say more substituted alkenes are more stable, it's all relative to what, okay? Your text uses heats of hydrogenation. That is, what's the stability of an alkene relative to its fully saturated counterpart. And that's the stability we're looking at, not necessarily the stability of the whole molecule. Yeah?
Small thing, why is that P minus P plus pi CH3? Because are you mixing it out of phase with the P minus P orbital?
Yes, I did that just so that I wouldn't have to redraw the molecule and write all of the phases. What you were saying would be minus P plus P minus pi CH3, and that's exactly the same thing. In the topmost orbital, we alternate phases, and so
I see. Okay, yeah.
on each, the wave function on each carbon has to have opposite sign. All right, good. Others? Questions? Go ahead.
Does ring strange change the stability at all of alkenes relative to the alkenes?
Does ring strain change the stability of alkenes relative to alkanes? It can. So,
We could.
and we haven't. There's an example of that I'll give you in a minute as we try to estimate the stabilization we get from aromaticity. So,
For example, you could imagine maybe 2 cyclopropene rings fused together along the double bond, and that would be tetrasubstituted.
right, you can imagine, and maybe that's in our, what Dakota is proposing is something like this, and maybe that's in our horror show of bad strain in the last lecture that we looked at. You can go look it up. My guess is that if that's known, it's horrific. And there's a whole sort of cottage industry, used to be in physical organic chemistry, of making the most strained rings possible. And there's a section at the end of chapter 2 that talks about these really tiny and highly strained rings. You have to care a lot to care enough to read about it, so we're not going to. If you want to, though, and if your life goal is to make really, really strained things, then I encourage you to read that, and I won't stand in your way. I might make fun of you a little bit, but I won't stand in your way. Okay, so delocalization. I guess I should mention there's a conformational effect here that is interesting for both alkenes and the corresponding carbonyl compounds. And that is the way, I guess now it's huge. Okay. The way I've drawn this is the most favored conformation. And it's, what conformations are even available? Well, think about rotation around that carbon-carbon bond, right? In this conformation, the proton here is sort of, if we were to look down, I won't draw the Newman projection, but I will draw the yellow Sith eyes. If we were to look down the carbon-carbon bond between carbons 2 and 3 here, what we would see is that these two groups are eclipsed, right? You'd think, why are they doing that? Eclipsed is bad. And the answer is the alternative has a weird sort of secondary orbital mixing effect that's unfavorable. So just imagine, again, this is the HOMO of one of propene. So imagine we make it so that the double bond is now gauche to those carbon-hydrogen bonds, and the other carbon-hydrogen bond is anti to the double bond. Sorry, I'm going to draw this orbital again. And because of the node that's here, you run into a situation where what you think might be more favorable from a steric point of view leads to an out of phase, unfavorable juxtaposition of the wave function. And that's enough to bias the conformation of the molecule in favor of this sort of eclipsed conformation. Okay? Yeah?
Why wouldn't we have a conformation where there's a proton pointing straight up and use the other 5CH3 orbital?
Could you have a conformation where, let's see, you want to do
Like one straight up and the other two.
so to do that, what would we do? We would here is a hydrogen coming straight out at you, and the other two are there.
Yeah.
And then you could use
The 5CH3 that uses all three protons.
I'm just, so everybody can see it, I'm going to draw what Jared's proposing, and then we can talk through it, because, I mean, oops, sorry, phases. Okay, so that sort of avoids getting these guys close to that in an out of phase relationship. And of course, you know, rotation around the carbon-carbon bond is free. There'd be some barrier, but certainly this kind of conformation would be populated. Let's see whether that works from a Newman projection point of view. Here's the double bond. Proton straight up. I don't know. That's a good question. I mean, we're basically asking, without all the orbital drawings, why do we go eclipsed here? Yeah. I don't know. Why is that lower in energy?
And is it legal to use the other 5CH3 like that? Doesn't it have to be orthogonal to H1, so you have to mix it with the other orthogonal p orbitals?
Yeah, I suppose a question would be, well, so there's no question at all that this is affine at any given time, right? The question is really, why is this arrangement the most stable one? Kim, it's possible that what you're saying is maybe the pi CH3 we've drawn here is, I mean, I guess you might propose that the pi CH3 we've drawn here is not as good at overlapping with this pi as it is with the other one that's in the plane of the molecule. Though the two pi CH3s are orthogonal to each other, or I'm sorry, degenerate. So I think it has to be the same either way. My guess, if I had to guess, is that this more favorable conformation keeps the maximum amount of things apart. In other words, maybe moving a little bit away from the double bond isn't that much better than being eclipsed with it. If you want to avoid it being eclipsed with the double bond, you have to approach the hydrogen on the other side more closely. I don't know. That's a good question. I'm sorry I don't have the answer to it. I think if we go look at our dynamic molecules, Can we find propene on our list and sort of see what, if we can get a sense for what the barrier to rotation is? LMNOP, PRO. Oh, there it is, propene. All right. So, I mean, that looks like the most stable conformation, though there's a bit of a wag. And there it went. And that's at 50 Kelvin. So, yeah, I think probably the preference is small. And I suppose the other thing you could argue from a hyperconjugation point of view is that if you keep this proton in the plane, both of these protons can align with and contribute to the orbital. Whereas on the other hand, I don't know. I'm hand waving. You can see me floundering to answer the question. So I don't know. I'll look it up. Get back to you, and you can hold me to that. Okay. Other questions on that? In any case, the barrier isn't high, so. Sort of watch it come to. And that's more like the conformation you're proposing, huh? Oh, okay. So what you're seeing is it doesn't take that much to rotate. I guess an interesting point is that as we talk about conformations, you need to remember that molecules are flexible. And anything, if we're talking about overall preferences, that doesn't mean that the thing is locked down and always looks like that, just that tends to be more stable. All right. So aromaticity we could talk about. Let's see. I'm going to copy some things from my notes because I don't think it's meaningful for you or me to draw a bunch of aromatic rings and comment that they're aromatic. I think this is mostly a review from 352. And there's more we could say about aromaticity from an MO point of view. We've already talked about the orbitals that are involved in aromaticity. We've already talked about the degenerate pairs of orbitals. Basically with aromaticity, you need to be cyclic, you need to be planar, fully conjugated, and have the right number of electrons. That number is 4n plus 2. The 2 comes from the fact that in aromatic systems you have one lowest energy orbital. That's the one where the pi orbitals are all in phase. And then beyond that, you've got degenerate pairs of orbitals, all the way up until perhaps you get to the highest orbital. And aromaticity consists of filling the bonding orbitals and completely filling the degenerate pairs without leaving unpaired electrons. Okay, so these first three examples, pyrrole, benzene, and furan, all have 4n plus 2 pi electrons. Hopefully you're good at figuring that out. Students in sophomore organic tend to struggle with which electrons to count and which not to count. So one of my favorite evil examples for my 352 students is imidazole. So who can explain to me whether this is aromatic or not, and which lone pair I count if one of them or not? Go ahead, Austin.
So it is aromatic because you can count the lone pair on the left nitrogen but not the right one.
Okay, so we count this one, these, and these, and we're going to put the big ekis on the other two. Why? Why don't we count those two?
Because the geometry doesn't fit.
Okay, right. That nitrogen is roughly again, a valence bond perspective, roughly sp2 hybridized. Based on the fact that that nitrogen's involved in a double bond, the p orbital is already accounted for. The lone pair has to be in an sp2 type orbital, pointing out into the surroundings. It cannot align with the pi system. It cannot participate. Oxygens are tricky too with furan. Why don't we count both lone pairs? Same reason, right? Okay. Aromaticity can also be used to explain why some carbocations are more stable than you'd otherwise expect. Go ahead, Dakota.
So if we were to draw extra resonance structures for imidazole, moving the lone pair in this double bond?
You could do that, but you would have to move the double bond over to avoid violating the octet rule.
And you would be making a carbene at that point?
No, it would just be a resonance structure of the...
Since you have a lone pair on carbene.
No, it would be more like a carbanion. A carbene would be, there would be no hydrogen there. Anyway, the resonance structure you're proposing is this one, and that one's fine. Not a major contributor perhaps, but that one's fine. Okay, aromaticity can explain why some carbocations are more reasonable than others. For example, your text actually points out that cyclopropene, cyclopropenium cation is more stable than the corresponding allyl cation. And you think, and that's just based on if you put a leaving group at that carbon, leaving group ability. Why is that? Well, you'd think there's ring strain there, but actually, and there is, but you've got the impact of aromaticity. I also look at this and I think it looks like a minion. Or if you've ever read Calvin and Hobbes, there's one series of strips where triangle-headed aliens, single-eyed triangle-headed aliens come down to talk to Calvin, and they actually interchange with him, and it's kind of funny. Anyway, if you don't know Calvin and Hobbes, you should look it up. It's kind of fun. But maybe you had to grow up in the 90s. Maybe it's not funny for everybody. Cyclopentadiene cation anion is a stable anion. You can use it as a ligand for transition metals, and it's just fine. The 7-membered ring is called a tropylium. I'm not sure how to spell that. There might be a Y there. Tropylium ion. I've been accused of drawing my 7-membered ring tropylium ions as looking like sad robots. So if we color him in gray, maybe. Aww, all by myself. Some aromatic systems, it's easier to see that they're aromatic once you consider resonance structures. This one is called Azulene. And actually, if you count electrons, 2, 4, 6, 8, 10, that's an allowed number. But if you draw the resonance structure where we move this double bond over and these electrons over, you get both a tropylium ion and a cyclopentadienyl anion in the same molecule. And indeed, the negative charge can be on, oops, that's entirely too large. The negative charge can be here or there. The positive charge can be here, here, or here. And it turns out, you can look it up, this molecule has a permanent dipole. And it's called azulene because it's blue. Also this particular ketone doesn't look like it's aromatic, but if you consider the resonance structure where you move these electrons out onto the oxygen, then it is. And you would expect that carbonyl to be more polarized than your typical carbonyl. there are examples of weird aromatic systems that violate the fully conjugated rule. And this falls in line with the sort of cute, but I'm not sure that useful observations. It sort of demonstrates principles without necessarily being that useful. But imagine drawing an 8-membered ring. And we're going to have 3 double bonds in it and a positive charge there, saturated carbon there. Can it be aromatic? Well, you would look at that and say, haha, that's silly because it's not fully conjugated. And on a 352 test, you would get the question right. But it turns out that if we take the carbon in red and we take our molecular salad tongs and reach in there and pull that thing up. It actually looks like some sort of horrible beast. Did any of you ever watch Homestar Runner? You know Trogdor? You don't know Trogdor the Burninator? Okay. You need to go look. I'm going to write it here in the notes. You can go look it up. Trogdor the Burninator. And maybe I'll draw him sometime. Figure out if he can come back. Anyway, look at this on the side. Imagine reaching in and taking that red carbon and pulling it up in a way that would bring carbon 7 closer to carbon 1. So this is going to be difficult to sort of draw from the side. No, that's 6. Sorry. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7. Oh boy. All right, let's put the kink point there. Here's the positive charge. One, 2, 3, 4, 5, 6, 7, 8. So now it looks like a sad robot with a bump on its head. So imagine now, I mean, it's clearly conjugated. It's just not fully conjugated. But if you can get carbons 1 and 7 close enough to each other, you can actually see indications for aromaticity. In other words, they observed that this cation is more stable than you would expect, even for a resonance stabilized cation. There's a little bit of extra aromatic stabilization. It's probably not a huge amount, but it was enough to convince reviewers at some point. Indicators of aromaticity are typically evidence for ring current in NMR. So you may know this, but protons that are, I'm going to draw a benzene ring as though it was on its side. One of the diagnostic NMR evidences for aromaticity is downfield shifted protons. We're talking about 7 to 8 ppm. Though, if you remember from learning about NMR, the ring current induces a magnetic field that it reinforces the external magnetic field that is applied at the position of the protons, but opposes the external magnetic field on the face of the ring. And so if you are in a molecule or a protein or some other situation that somehow puts a hydrogen sitting over an aromatic ring, you can observe the hydrogen in this area above and below the aromatic ring as being shielded or upfield shifted. So you're de-shielded on the outside, you're upfield shifted on the inside. All right, yeah.
Do you know if they ever ran an MR on Sad Robot with bump on its head?
Did they ever run an NMR on Sad Robot with bump on its head? Probably. I don't know what the reference is. It's called homotropilium cation. And why not? I'm going to Google homotropilium ion instead of Sad Robot with bump on head. Um, 1959. Let's see. Early evidence, blah, blah, blah. So another example of, they call this, it's called homoaromaticity. I don't know why, but it refers to aromaticity in not fully conjugated systems. And another example that your text mentions is this one, where you put the tosylate leaving group leaves, you have a cation here, and then you have this single bond here that can then do resonance. It's like you've almost got a cyclopropane type system, and there's evidence for aromaticity there. It looks like they're looking for coplanarity if you've got a structure, measuring stability, and then NMR. There we go. So that's the clear indicator. This is Sad Robot with bump on head. If that thing is kinked up, one of the protons is going to be in the shielding region of the ring, and the other is going to be in the de-shielding region of the ring. And that's, I mean, negative chemical shifts are sort of unheard of except in that context. So that's pretty unambiguous evidence. Cool. We all learned something. One of the skills you should be gaining as senior undergrads and grad students is the ability to Google things and sort through the information and figure out the answer. Because half the time, the little secret, don't go telling my colleagues. When people show up in my office and ask me questions, half the time I'm like, let's Google that and see what the answer is. So it's not about knowing facts necessarily, but how to interpret things that you read, I guess. So how good is aromaticity? And an answer for that can come from what are called isodesmic reactions. This is where you set up a pretend reaction where you keep all the all the kinds of carbons and hydrogens constant. So it'd be difficult to see without going through it in a lot of detail, but if you compare the 3 cyclohexene molecules we're starting with the benzene and 2 cyclohexane molecules, we've got the exact same number of sp3 hybridized carbons, sp2 hybridized carbons, and carbon-hydrogen bonds on either side of the equation. So ideally what we should be seeing would be just the contribution to aromaticity. And if you, based on heats of formation, calculate the change in enthalpy for this pretend reaction, you get about 36 kilocalories per mole. And then you have to correct that for strain that exists in the cyclohexene that is not present in either benzene or cyclohexane. And the answer is about 32 kilocalories per mole of stabilization. So that's enormous. It's almost almost worth an entire extra pi bond. So that's kind of fun. Let's see. In polycyclic, there's some stuff in the book about polycyclic aromatic hydrocarbons you should look at and how to count electrons. Yeah, Dakota?
Yeah, when I took 352 from you, I think we walked through all the orbital diagrams and
Uh-huh.
alpha and beta values, and
Yeah.
the enclosed conjugated ring was like an extra free bond.
An extra beta, yeah. You can do Huckel analysis. We didn't do this in chapter 14 because it's not used a lot anymore, but you can do Huckel analysis to figure out just exactly how much more stable benzene is due to aromaticity, and it's almost an entire additional pi bond. Some things to know about polycyclic aromatic hydrocarbons. This is anthracene. If you were to draw that on a sheet of paper, you might be tempted to conclude that it is flat, and it is, but it's also flexible, right? And depending on the situation, for example, anthracene, and then if you take away one benzene ring, you've got naphthalene. If you expose those to electrophiles in general, they don't do addition chemistry. I'm going to just briefly remind you that when you expose benzene to bromine, nothing happens until you add a Lewis acid, and then you get substitution chemistry. We do not get addition chemistry like you would get for an alkene, right? So that's true for both benzene, naphthalene, and anthracene. But if you take the benzene ring on the end, I'm tripping over my stupid bag. You take the benzene ring on the end and move it over just sort of one carbon, you have something called phenanthrene, and that one's weird. I'm going to see if we can find it here. Nope. Sorry. Incidentally, the reason they call it anthracene is I think it must have first been detected in coal, which is sometimes called anthracite. Phenanthrene is when you link the three benzene rings together this way. And it turns out that for phenanthrene, this double bond behaves as though it were an isolated double bond, and you have lovely aromaticity here and here. And those rings, nothing happens to them, but if you add bromine to phenanthrene, you get bromination on that double bond in the central carbon. So it can be somewhat difficult, especially with polycyclic systems, to determine which rings are fully aromatic and which aren't. And in general, you look for, actually, I'm not sure, just even looking at the phenanthrene structure, that it would be obvious that this would happen. So as you get bigger, as you get rings that are bigger, sometimes you don't have extended aromaticity in all of the rings, and sometimes they can be reactive. And just as a final point, the central ring in anthracene is known to be a decent diene in Diels-Alder reactions, because you can do a reaction there and still have aromatic rings on either side. All right, that was somewhat hurried, and I'm sorry. We'll keep cranking in chapter 2. I think we'll need one more lecture, and then we'll be done. So have a great Wednesday.